So using this fancy plug-in electronic galvanometer set to the most sensitive setting, so 100 volts, and this one, I can then get a bar magnet, and so all I have here is a long bit of wire, and I can actually just move that in the Earth's magnetic field, and you're seeing a change there. So if I'm moving it backwards and forwards inside the Earth's magnetic field, and vertically versus horizontally seems to have a larger effect. So you can start with that, and then you can just get a simple bit here and just put a magnet through it, and you're seeing that there is some deflection. And you can say, well, how do I make that stronger? What is if I change it from being a single loop to being a double loop and put a magnet through, and you're seeing a much larger deviation. And then you can do the same thing here with a stronger magnet, and so you can see that effective B is quite big, and so I can click it up a setting and do it the same. Or I can do it just with a wire, and it's not that effective with one loop. Stronger, and then I've got it around 3 times, and you're seeing quite significant deviation. So significant, well, moderately significant current being induced. And so you can then wrap that up 10 times, 20 times, and go, well, what's a better way of doing that? And then say, well, that's why we've got a solenoid. And so you're saying that cross-sectional area or number of turns has an impact on the voltage being induced. You're then also saying that velocity does, so the faster you do it, the greater the change in flux over change in time, the larger the EMF induced, or the larger the magnet. So then you can use the horseshoe magnet and then get even larger outcomes. And so that's a good introduction to Lenz's Faraday's law on electromagnetic induction.